Hi, I'm Cullen. Welcome back to Module 6 of Networking Fundamentals. We're going to get started here with understanding Internet Protocol, or IP, as everybody likes to call it. All right, let's go and take a quick look at our agenda. We're going to go ahead and cover two objectives today. First one, 3.2, understand IPv4. Within that, we're going to detail IP version 4 or IPv4. We're going to talk about the address categories for the protocol, talk about network address translation, then move on to discuss default gateways and DNS servers, and then finally touch on subnetting and CIDR. Then lastly, we'll go ahead and touch on IPv6 as well as a protocol, the ultimate replacement or the eventual replacement for IPv4. Okay. The Internet Protocol resides on the network layer. Go ahead and recall that from our detailing of the OSI model. IP addresses are used to help devices send and receive data across networks. Remember that they are very much like our mailing addresses. So if you mail something to your mom or you mail something to a friend, same way computers communicate, they use addresses in order to make sure that information goes to its intended destination. IPv4 currently is the most commonly used communication protocol, but IPv6 is starting to replace it, and it's already being used more widely and widely everywhere. Okay. All right, so let's talk a little bit more about IPv4. So this is the fourth version. That's why it says v4. It's the first version, though, of the IP protocol to be widely used. IP addresses consist of 4 octets. All right, so we have 4 octets, and we touched on this briefly in a previous presentation, but super important to know, okay? So you got 1, 2, 3, 4. We have 4 different examples here. Each has 4 octets. Each octet is separated by a decimal point. You may refer to it as a period, but call it a decimal for this sake. Each octet represents 1 byte, or 8 bits, meaning that an IPv4 address features 32 bits. So what that also means is that we can convert those decimal values into binary. So let's take a look at a simple octet here. Let's say 192 as an example, okay? We'll go back to this chart. If I take a look at the number 192 as an octet, and I say, hey, I want to convert this into binary. What I can do, if you take a look at this chart here, is if 128 as a value fits into 92, then I can go ahead and I can put a 1 here and say yes, I can in fact subtract 128 from 92. So if I do that, do some math. Probably wishing I was using a calculator right now, aren't you? What we end up getting is 64. Well, so now my leftovers, 64. Can I subtract 64 from 64? The answer is yes. So I'm going to go ahead and I'm going to put a 1 right here. And if I do that, 64 minus 64, all of a sudden I have 0 left. You might be bummed out that you have 0 left, but it's okay because it actually makes the rest of our job very, very easy. I'm going to say, hey, can I fit 32? Or rather, can I subtract 32 from 0? Well, no, there's nothing there remaining, so all of a sudden I put 0. The answer is no, and that's what 0 represents, is no, or false. Same thing with 16. I've got a 0 there. There's nothing remaining, so I can't even subtract 8 or 4 or 2 or 1. And so, of course, my decimal equivalent for this would be 192. And if you take a look at the examples up above, say for 224, we did the same thing here as well. So you see, we can subtract 128 from 224, and then whatever's left over, we can subtract 64 from that. And then, of course, we would only have 32 left over if we did that, which means that we put a 1 here, and then the rest are all zeros. And that's how we would translate decimal into binary, and also vice versa, how we can take binary and translate it into decimal, okay? Great job. If If that was a little hard to follow, I would definitely recommend that you go ahead and Bing decimal to binary conversion or IPv4 decimal to binary conversion. Really quick thing for you to do. There are a ton of really great tutorials out there. There are also some packets that you can find if you want to practice. Definitely helps out a lot. All right, so let's go on. Let's talk about IPv4 address categories. There are 5, and they've been categorized, or pardon me, they've been categorized into 5 different classes, right? The classification system, it's called classful addressing or classful network architecture. And in this system, the first octet of an IPv4 address defines which class the address belongs to. So if the first octet is in the range of 0 to 127, then it belongs to class A. If it's in the range of 128 to 191, then it's in class B, and so on and so on. So I'm going to show you a quick little trick for remembering these IP class ranges, okay? If you convert the first octet into binary, and the very first digit is a 0, then you know it's class A, because 0 means that you couldn't subtract 128 from it, right? And if you have 127, you can't subtract 128, can you? So now watch, because there's a little bit of a trend here, okay? And I don't want to spend too much time on this, but I think that this is really helpful, and I wish somebody would have taught this to me when I was learning. 128, we can subtract 128 from that, so there we go, right? But if we have 128, and then if we looked at that second digit, if there was a 1 there, that means that we would have 192. Well, the range only goes to 191. So what that means is that this second digit has to be 0. So just like we had the first digit for class A addresses in the first octet had to be 0, the second one in class B addresses has to be 0. Now, if you take a look at C, the third digit has to be 0. And that's because if that was a 1, then the lowest possible number that we could have within that range would be 224. So now we go on and we look at D, and you guys are like, man, this is no longer rocket science. This is pretty easy stuff. It's that fourth digit is 0, and then all of a sudden E is everything else, where you start with that fifth digit as 0. But notice here that that last digit's 1, and that's because we reach the top of our range. And I don't know if I explicitly mentioned it. It should have been featured on one of the slides, but I will definitely tell you that octets, they have to fall in the range of 0 to 255, okay? Really important stuff to know. But hopefully that was helpful in terms of remembering how the classes are organized. It's a really challenging thing, so if you are having troubles with it, don't be too hard on yourself, okay? All right, so one thing about Class A is that there is a reserved network address for loopback IP addresses. And loopback IP addresses are used for testing and ensuring that that your network adapter is properly functioning. Every device is automatically assigned the 127.0.0.1 loopback IP address. A funny way to remember this is I have one of my friends who has it's supposed to be like Home Sweet Home, but it says Home Sweet 127.0.0.1. Just referring to the fact that that's the IP address, the loopback IP address that always points back to home. Okay, sort of geeky, but if you Google it or if you Bing it, it'll probably come up. All right, so IP addresses also have subnet masks, and we did talk about that a little bit earlier. And each IPv4 address has a network portion and then also a node portion. Just for reference sake, a node is another word for host, by the way. There are a lot of different vocabulary words that we use interchangeably. So if you get confused, once again, don't feel bad. Just make sure that you go ahead and take time to clarify. It's really important that we get these things and these concepts and ideas organized in our heads. All right, so with Class A addresses, the default subnet mask is 255.0.0.0. And so what that means is that if you have 255, that portion belongs to the network. In contrast, if you have zeros, then that portion belongs to the hosts, right? So that helps uniquely identify a host or a node. So similarly, if we take a look over here at our subnet masks for Class C addresses, the first 3 portions are dedicated to the network. So that information in an IPv4 address is used to determine which network or identify which network a host or a node belongs to. And then that last portion is to specifically identify that unique device. All right, so within these classes, there is a number of addresses that are a number of usable addresses that are available for computers, okay? If you take a look at the chart down at the bottom, we look at the total number of networks and then the total number of usable addresses. So we raise 2 to the 7th power because if we look at an octet, and I'm just gonna draw all zeros here, so don't hold that against me. We have the first one is listed as 0 because 2 to the 0th power is 1, right? And then the next one is 1, which would place us at 2, and then the next one is 2, which gives us 4. Next one's 3, which gives us 8. Next one is 4, which gives us, next one's 4, which is going to give us 16. And then we have 32, because it's 2 to the 5th power. 2 to the 6th power would give us 64. And then 2 to the 7th power gives us 128. And so if that happened to confuse you, I'm going to go back here just to show you real fast at our decimal to binary conversion slide. This is where I was getting those values from, right? So here we have the first digit, the second digit, third, fourth, fifth, the sixth, the seventh, and then the 8th. And that's the power. These are all the powers that we would raise to as we move along digits, right? So it's 2 to the 0th power because you have 2 options in binary, 0 or 1. And so you're raising it to the 0 power, and that's how you get the value of 1, and so on and so on. Once again, that could be really, really confusing if this is your first time looking at this stuff. So if you do need to pump the brakes and you go need to do a couple of searches in order to better understand this stuff, don't feel bad. So going back to what we were saying, the total number of available network addresses is 128 in a Class A network. The total number of usable host addresses, however, 16,777,214. There are actually 2 more addresses that are available, but they're not usable because the first address is reserved for the entire network. So that becomes the network address, right? It's used by the default gateway, which is a router that's going to serve as the gateway, no pun intended, to the internet for your local area network. And the last address is used for a broadcast address. And that's used when a device wants to communicate with all devices on a network. So make sure you take time to go ahead and study this chart and prepare yourself to recall the total number of usable addresses, and always remember that it's the total number of addresses minus 2, because you're going to subtract the 1 for the network address, right, the default gateway, and then 1 for the broadcast address as well. Okay, all right, let's move on to the next slide. Next, we've got public and private IP addresses. IPv4 addresses are further classified as public or private. And public IP addresses are just the ones that are exposed to the internet that anybody can see. And then private ones are hidden from the internet and any other networks. And so you've got private ranges here in this table on the right. And so you'll see that commonly, I bet if you probably checked your IP address right now on your computer, it would come up as 192.168.0.0. For larger organizations, it's going to start with a 10. For medium-sized organizations, it'll probably start with 172.16 if you happen to be on a network, a local area network right now. My apologies. All right. Next, there are also static and dynamic IP addresses. So IP addresses can be assigned statically, which means that they're manually assigned to a host, and so they don't change. That's what static means that it doesn't change. Dynamic, in contrast, means that it does change. And so with these types of addresses, we automatically obtain them from a server, which is pretty darn cool. So, if you're moving from location to location, you're probably having IP addresses assigned to you automatically, and you may not even be aware of it. This is something that completely just, gave me a headache, made my head spin when I was first learning about this stuff. So, all right. There's another reserved range for, or another reserved network, right? For it's in Class B. It's called Automatic Private IP Addressing, or APIPA, right? If a client can't get an IP address from something called a DHCP server, which is Dynamic Host Control Protocol server, and an IP address hasn't been configured statically, then it auto-assigns this number to itself on the network. So it'll have an address within the 169 range. This is useful because if your computer can't access the internet, or there's something wrong and you can't automatically obtain an IP address, then you're going to self-assign an APIPA address, and then that'll allow you to communicate with all the other devices that are on your local network. All right. Network address translation. Let's go ahead and move on and talk about how public and private addresses really function and how they work out in the open, out in the wild, if you will, right? Network address translation is just simply the process of modifying IP addresses while in transit across a traffic routing device. So what happens here is that this, let's see here. So we might have computer 1 sends information to a switch. The switch goes ahead and sends it off to the router. And then what happens is that packet might have the addressing information of 192.168.0.255. And what's going to happen is that there is, and this is my translation process here, right? That router is going to go to work and it's going to translate this address into this one. It actually knows exactly what that address is, so the process isn't as messy as that, but I just thought it'd be more fun if I scribble on the screen. And so everybody that's out in the internet, right, this cloud here, they're going to see this public-facing address. They're never going to see the private address that's being used by the computer on the local area network. And this is a really cool process because what it does is it makes it a little bit easier for us to use IPv4 addresses. I guess I should have said that IPv4 addresses are limited. We actually have more devices than available addresses with IPv4, which is a huge problem. And so this allows us to make better, more efficient, more effective use of them. So, all right. And of course, here's a little bit more information on NAT, right? Stuff I just said. It was developed to provide a temporary solution to the shortage of IPv4 addresses. So. Okay, so let's talk about default gateways and DNS servers. For a device to be able to access the internet, if you're on your computer right now, it has to have a default gateway, and you also probably will need a DNS server unless you are really good at remembering and recalling IP addresses. Default gateways provide default routes for TCP and IP hosts, right? Our computers, our devices, to use when communicating with hosts across the internet. So anytime you send a text message, this process, default gateway is probably being used. The first IP address of the device that a client computer will look for is actually the address that belongs to the default gateway. And so this network address that we were talking about, the first address in a network range or on a network, is going to be assigned to a router. All right, that router is and it does serve as the default gateway. So keep that in mind. Here's a little data going through the router and then, of course, onto the internet. It's pretty exciting stuff, this data transfer. Let's talk about the domain name system, okay? If, let's say we want to go to Bing, okay? So I'm on the laptop and I want to go to www.bing.com. Well, that server that's located over here on the top right, that has all of the good Bing HTML files and all the other code that we need in order to create the Bing.com web page on our screen. And so what we need, though, is we need something to take that name and translate it into an IP address so that we can access the Bing server, because it's not called Bing.com. The server actually has an IP address. And so let me actually erase the ink, because I think my animation is going to cause me troubles and make me back up with what I just said here. But let's now pretend that that's not the Bing server, but it's actually a domain name system server, okay, a DNS server, right? And so what's going to happen is we're going to type in bing.com into our browser, and then that information is going to be relayed to the DNS server. And then what happens is that DNS server is going to send us back the IP address for bing.com. That's the actual IP address for Bing. And if you type that into your browser right now, you actually should be able to access Bing without typing in the name. But what it's going to do, what that DNS server did, was it translated that name into an IP address that we can then use to access the web server where Bing is located. All right, so lastly in our voyage through subnetting through IPv4, we're going to talk about subnetting and CIDR. Subnetting is simply the act of dividing a network into smaller subnetworks. It's similar to taking a big old pizza and cutting it into slices, and the size of those slices differs based on the objective, right? You can make bigger or smaller slices. By default, all computers are like one big pizza. They're just one subnet or network with no divisions involved. So we have to make sure that we subnet them. That's where the term subnet comes from, by the way, in order to make sure that we efficiently use our IPv4 addresses. All right, so with classless interdomain routing, if we take a look here at our slide again, it's intended to replace classful IP addressing, and it has, because we once again want to slow the exhaustion of IPv4 addresses. We don't want to run out. We want all of our devices to be able to access the internet and communicate with each other. It's based on something called variable length subnet masking, and that allows us to divide a network into those different size subnets. To implement VSLM or VLSM, what happens is networks borrow bits from the host portion of an address. So if you have 32 bits, like if we looked at a class A address, if you had 8 bits that were for a host, 8 bits for a network portion, and then you had the other 24 bits that were for a host, that Class A network could borrow bits from the host portion in order to create subnetworks. So pretty cool stuff. We're not going to go too far in depth right now. In fact, not much further than this with VLSM, but I would definitely take a look at this online. Go ahead and do a quick Bing search to learn a little bit more and find out more about subnetting. So, all right. On to IPv6, Internet Protocol version 6. This is the wave of the future, and actually it may even be the wave of now for some folks. Not everybody's implementing IPv6 yet, but it will happen very, very soon. Okay. Internet Protocol version 6 is just a new generation of IP addressing. Solves a lot of the limitations with IPv4. The difference between the two is that IPv6 is 128 bits, while IPv4 is 32 bits. And so IPv4 is approximately just 4.3 billion IP addresses. All right, that's the result of 32 bits, whereas 128 bits results in 340 undecillion addresses. And if I wrote out all the zeros in an undecillion, let alone 340 undecillion, I'd be writing for a really long time. I encourage you to look up how many zeros that is. It's pretty cool. And in fact, it's enough addresses to give an address to every single grain of sand on Earth right now. And that is just mind-boggling, absolutely mind-boggling. I had a student tell me once, they did some calculations. They said that not only is it enough for every cell in every human body in the world to have an IP address, but each individual on the planet could also have 500 extra addresses for all, or 5,000 extra addresses for all their devices. I might have messed that up, but I thought that was a pretty cool statistic, whether it's true or not. And so IPv6 addresses, they're represented differently from IPv4 addresses. They're actually 8 groups of 4 hexadecimal digits. And so here we have a sample of an IPv4 address, okay? There's a site prefix, so the first 3 groups, these right here, make up the site prefix. Then we have a subnet ID, which seems much simpler than our subnets with IPv4, right? Maybe not. Then we have an interface ID, which is the actual host portion of the IPv4 address. All of these zeros, they can be condensed using semicolons, just like that, right? So you might see these condensed as 3 semicolons in a row and then 68. So cool stuff. Note here, there are periods for some reason. I must have been making this slideshow really late at night. Right. So how do we get these 2 protocols to work together? How do we get them to live together? And the reality is that sometimes we just frankly have to use both protocols. There's a dual IP stack that allows us to use IPv4 and IPv6 at the same time. We're not going to go into great detail on this here, but it's definitely something that you just want to be aware of as you move forward in preparations for the networking fundamentals exam. Okay. We can also map IPv4 addresses to IPv6 addresses. And so what happens is that instead of a normal structure for an IPv6 address with those hexadecimal characters, the last 32 bits of the IPv6 address are written in just that customary dot decimal notation. And so if you look at this here, we have an IPv4 address that's just written as, it's written with the hexadecimal characters. Note that we got those 2 semicolons showing us condensing, right? And then we just feature the IPv4 address for the last portion of that IPv4 mapped IPv6 address. Okay. So it's amazing what computers can do and how much goes on behind the scenes that we're not even aware of. And so what happens here is that, just to continue on with our discussion of IPv4 mapped addresses, IPv6 packets are encapsulated inside of the IPv4 datagrams. And then with Microsoft, it's done with something called a Teredo adapter, which is just a virtual adapter or sort of a logical interface, a pseudo interface here on the screen is what it says. And an example of these addresses is just located below. So this is kind of crazy, but what happens is we basically take an IPv6 packet and then we just wrap it inside of an IPv4 datagram, send it along, and then that pseudo interface, that adapter, that virtual adapter, is going to go ahead and unwrap the IPv6 packet, and then data is going to move along with processing. Okay. All right, so that's the end of our voyage through the IP protocol. We talked about two objectives today. We had 3.2, understand IPv4, and we had 3.3, understand IPv6. We didn't get into a whole lot of detail on IPv6, so I strongly recommend you do a lot of research on your own. I mean, this stuff, you could just learn about it for the rest of your life, and you wouldn't be out of information to learn. So don't be afraid if this seems like it's challenging or if it's hard. It definitely is. And that's part of what makes it so beautiful and so wonderful and so exciting to learn. So thanks again for joining me. I'll see you guys during our next module. Bye.